Welcome. You know, when I die, I want to go peacefully in my sleep, like my father did, not screaming and yelling like the passengers in his car. Anyways, let's talk about some math, guys. Kinetics, rate laws. This is where the math comes in calculating the speed of reactions. So let's get rolling on this. Reaction rate laws are equations that express the mathematical relationship between the rate of a chemical reaction and the concentration of the reactants. This is called the rate law. For example, in a simplest reaction I can think of, hypothetically, we have A turning into B. We have this reactant turning into this product. The rate law will always be expressed in a format like this. It'll always be the rate of the reaction, how fast the reaction's going, will be equal to a constant. K will be a constant times the concentration of A. It's important to note that these brackets are not parentheses. When you see brackets around a chemical, that represents the concentration of that chemical, and normally we measure that in molarity. So the concentration of A times a constant will be the rate of the reaction. K is a specific rate constant, so K will vary for every reaction and actually every temperature. The reaction is directly proportional to the molar concentration of A. In other words, if you double the concentration of A, so let's just say the constant is 1. So 2 times 1 is 2. And then I make it 4. 4 times 1 is also 4. So as I increase or decrease the concentration, that will be directly affecting the rate. If the concentration of A doubles, the speed of the reaction would be twice as fast. That's the layout. Rate equals a constant times the concentrations of the reactants. The K, the constant, is a numerical constant that relates to the reaction rates and the concentration of the reactants at a given temperature. So if the temperature changes, the K value changes. And like we learned before, if you have if it's hotter, the reaction will go faster. So there'll be a different K value that takes into consideration temperature. The concentration will be multiplied this value, and like I said, it's a numerical value that relates the concentration to the rate. Because it's kind of an in-between to go from concentration to the rate, the constant for K has unusual units. It doesn't really make a lot of sense, and actually every rate law can have a different kind of a unit arrangement for K, and we'll talk about that at the end of this lesson. So if you have a large value for K, that would mean that the reaction will quickly form B. So if in this reaction here, if K is a large number, that means B will form fast. So this is a quick reaction if K is large. On the other hand, what does it mean if K is small? So what does a small value of K mean? Well, I think you should be able to figure that one pretty easy. That would mean that the reaction is going to be slow. So the reaction will be slow with a small K value. Reaction will be fast with a large K value. Okay, so we understand the equation. The basic write-up is rate equals K times the concentrations. We understand that what K is, it's the constant, the go-between. Now let's talk about the different things, the different ways that the concentrations can be affecting, the reactants can affect this. And so the reactants have a different order. And so I'm going to give you the first example of first order, and it's actually kind of what we did in the last one. That was a first order reactant. A first order reactant, as the concentration changes, it's directly related to the rate. So if you increase the concentration by 2, the rate will also increase by 2. So no matter what K is, if you double A, it will also double the rate. This is a first order reactant, as opposed to a situation like this. This is a second order reactant. In second order reactants, if you double the concentration, instead of making the reaction go twice as fast, the reaction goes 4 times faster. So with second order reactants, what you see here is the concentration of A is squared. where in a first order, you could think of a superscript of 1 here. So it doesn't change anything. This concentration goes directly related, where in this one here, the concentration would be squared. So stop and think for a moment. If I double the concentration, it quadruples the rate. If I triple the concentration, what would happen to the rate? If I triple the concentration, a lot of people will think that the rate goes up 6 times. That's not true. It's squared. So if I triple the concentration, the rate will go up 9 times faster. So that's second order reactions. It's exponentially faster. This is an example of a rate law with an actual reaction. This is nitrogen monoxide and hydrogen will react to make nitrogen and water. 2 moles of nitrogen monoxide reacts with 2 moles of hydrogen to make 2 moles of hydrogen to make 1 mole of nitrogen and 2 moles of water. The rate law for this reaction is as follows. The rate equals the constant, which is, we'll get into that, a constant, that's particular to the temperature, times the concentration of nitrogen monoxide squared times the concentration of hydrogen. In this rate law, what I want you to note is that the nitrogen monoxide is a second order reactant and the hydrogen is a first order reactant. Changing the nitrogen will affect the rate dramatically to an exponential power of 2, where changing the hydrogen will directly change the rate. So doubling the hydrogen will double the rate, but doubling the nitrogen monoxide will quadruple the rate. I show you this with a real reaction because I need you to think and get over some misconceptions here. Notice that these stoichiometric coefficients, the 2, a 1, and a 2, have nothing to do with the rate law. Some people will get confused. They'll see this 2 and they'll want to make that second order, and they'll see this 2 and want to make this second order. That's not true. And so kids or students will look at this and say, well, how do I know the rate law from this equation? I don't see it. Correct. You don't see it. The balanced equation, that stoichiometry, has nothing to do with rate laws. So I'm showing you this to tell you that this equation, what the coefficients are, it doesn't matter. It doesn't matter that there's a subscript here too. It doesn't matter that there's a nitrogen and oxygen. None of that matters, okay? In this situation here, I gave you the rate law, and we'll go further with this, and I'll show you how to figure out the rate law, but you will not be able to figure out a rate law just from an equation. That's not possible. The last type of rate law that I want to talk to you about is a zero order. In a zero order, if you increase the concentration of a zero order reactant, the rate is unaffected. So you can double the concentration and the rate doesn't change. Or you can decrease the concentration and the rate doesn't change. As long as this reactant is available, the reaction will continue to go, but it doesn't affect the kinetics of the reaction. I think of this like a candle burning, and think of the wax. The amount of the wax, I'm saying amount, but concentration, but just this is my analogy. The amount of the wax, as the candle's burning, as you lose more and more wax, it doesn't make the reaction go slower. And when you have a lot of wax, it doesn't make the reaction go faster. So the concentration is what I'm talking about here, not the amount of the volume. But anyways, the concentration does not affect the rate. So if the concentration of it doesn't make it go faster, then the rate doesn't change. So that would be a zero order. I hope I didn't confuse you too much there. So let's just make it simple. If you have a big candle, a lot of wax, that doesn't go faster than if your candle is almost burned out. The reaction goes the same. That would be zero order. Okay. So let's look at a math problem and figure out how we answer it. A rate law problem will look like this. It's going to be data. I'll give you some equation, or the book will, whatever. You have some equation, and I'm just saying A plus 2B's and plus a C makes D. Remember, these coefficients don't matter. But what matters is there's 3 reactants. How you solve rate law problems is through experimental data analysis. So we did 4 experiments with this reaction, and in each experiment we change the concentration of things. So we can see that the concentration is varying of the different reactants throughout this experiment. And as we change the reactants, we also time the experiment. We see a rate that D was forming in a certain amount of molarity per second. Okay. So the first thing you have to do when you look at an equation like this, because it's confusing, you're like, okay, so well, what I mean by it's confusing is the question is, I'll give you data like this, and the question is, what is the rate law for this reaction, and what does K equal? So you have to be able to gather that from this information. So let's walk through the process now. The first thing you got to do when you take a look at this information is look how the reactants change and compare them with the products that are changing. So look at how the reactants are changing, these values are changing, and look at how that affects the concentration of our product. Based on your observations, try to find instances where only one concentration is changing. You have to kind of figure out finding examples where you have three variables in this one, A, B, and C. You have to find a situation where only one of the variables is changing, because you can't make a conclusion if multiple variables are changing. That's basic science. Sometimes I see advertisements for diet pills, and they'll say like, hey, take the diet pill and you're going to look great. You're going to lose a bunch of weight. And then in fine print it says, take the diet pill along with proper diet and exercise. Well, you know what? That's three variables, and you can't make a conclusion based on three variables. Does the person lose weight because of the diet pill? Do they lose weight because of their diet? Or did they, don't want to use this finger, or did they lose weight because of their exercise? Which one of these and was the factor, or were all of them factor, and by how much? So you can't say the diet pill made them lose weight if you have other variables that were changing as well. So if they say, take the pill, don't change your diet, don't exercise more, and you're going to lose weight, that would be one variable, and that would be more scientifically founded. So with that idea, our conclusion, we can say losing weight, or the conclusion of the production of D, is going to be based upon the change of these concentrations of both A, B, and C. So if we take a look here, let's figure out which experiments would we use to determine how A changes the rate of the reaction. So if you look at the first two, you see that A didn't change, so that wouldn't be any good. If you look at the next two, A didn't change. So if we look, let's just say 3 and 4, we see that A did change. Okay, so maybe this change is because of 3 and 4. But we have to make sure that B didn't change. And take a look at this. B does not change. We've got to make sure C doesn't change. C doesn't change. So B's concentration is the same. C's concentration is the same. But we doubled the concentration of A here. So the change in this reaction with between 3 and 4, the change in the rate of reaction is completely to do with A, because the other variables were controlled. So what that's saying is, for reactant A, we would choose experiments 3 and 4 to analyze the effect of A on the rate of the reaction. To analyze the rate of the effect of the reaction from B, let's take a look here. If we did 1 and 2, we can't because B is the same. So let's look at 2 and 3. Okay, A is the same, B changed, but also C changed. So I can't use 2 and 3 to analyze B because both B changed and C changed. So that's not going to work. Let's take a look at 1 and 3. A is the same, C is the same, and B went from point 1 to point 2. So if we use experiments 1 and 3, we can say the change in rate of the reaction is only because of B, because A didn't change the rate of the reaction. C didn't change the rate of the reaction because it was the same in both times. The only thing that was different was the concentration of B. So we can say that the change in this reaction is because of B. And the last one, how about C? What do you think C would be? And I would say, let's take a look at 1 and 2. If you look at 1 and 2, A is the same, B is the same, and if you look at C, you see that C has doubled in concentration, but A and B are the same. So the rate change between the rate change between 1 and 2 is entirely due to the concentration change in C. So we figured out that the reactant C we will use to determine the concentration, the effect of C on this reaction. We're going to use experiments 1 and 2. That's the first thing you have to do, is figure out how we're going to analyze A, B, and C. What part of our data will we use? And to figure that out, again, find where A is for A, where A is changing, but B and C are the same. Find for B where B is changing, but A and C are the same, and finally where C is changing and A and B are the same. Now that we know which ones to use, let's figure out what order these reactants are. So we said that for A, we're going to use experiments 3 and 4. Okay, so we're going to use 3 and 4. As the concentration doubles, see this? It went from 0.1 to 0.2. What happened to the rate? The rate went from 0.02 to 0.08. So as the reactants doubled, the production rate quadrupled. So how do we plug this in mathematically? Well, we say that the concentration doubled for them and the rate quadrupled. The order of the reactant the order of the reactant is the exponent. So 2 to what power is 4? And you should be able to figure out that 2 squared, or 2 to the second power, would be 4. That means that this is a second order reactant. A is a second order reactant. So our rate law is going to start making some shape now. We know that the rate equals K, and A is a second order reactant. We have to do the same thing for B and the same thing for C. So let's figure out the order for B, and then we'll figure out the order for C. With B, we said that we're going to use experiments 1 and 3. Between 1 and 3, remember A is the same, B was this, or C was the same, but B went from 0.1 to 0.2. So using 1 and 3, we can say that the rate is only because of the change in the concentration of B. It went from 0.01 to 0.02. So as the rate doubled, so did the concentration. So as the rate doubled, the concentration also doubled. So 2 to what power is 2? Not too hard. 2 to the first power is 2. This means that B is a first order reactant. B is a first order reactant. So our rate law is starting to form here. Rate equals K times A squared times B. Let's figure out the order of C now. In experiments 1 and 2, we have C changing. A is the same, B is the same, C changed. So the change in rate is completely due to C's change. We see that as C doubled here, the rate didn't change at all. So as the concentration doubled, the rate had no change. It's the same value. So 2 to what power is 1? And anything to the power of 0 is 1. So anything to the power of 0 is 1. So therefore, this is a 0 order reactant. The presence of C is necessary for this reaction to occur, but its concentration has no effect on the speed of this reaction. So therefore, the rate would be equal to K times A squared times B. This is the rate law for this reaction. And we're almost done. So we just figured out the rate law. The next thing is, what does K equal? What does K equal? To solve for K, choose any one of the experimental data points. I'm going to use experiment 3, but you could use 1, 2, 3, or 4. You should get the same answer no matter which one you use, and I highly encourage you to try another one and check my answer. And especially on a test or quiz, do more than one experiment to make sure you're getting the same answer, as long as there's time permitting in a test or quiz, just to give yourself a little insurance that you're sure that you're getting it right. So we're going to use experiment 3 in this, and we found that in experiment 3, these were the concentrations, right? This is just right from my data table, and I just determined the rate law. The rate law was the rate equals K times A squared B. Remember, C is not there because it's 0 order. All you got to do is take the data points from one of your experiments and plug them in. We know what A is, we know what B is, we know what the rate is, so let's solve for K. Rearranging this equation, I would cross multiply, bring A and B down, so it would be rate over A squared B squared, and that would be, the rate would be in molarity per second, and I've got 0.1 molar squared times 0.2 molarity. So I got molarity squared and molarity, so I have 3 molarities on the bottom, but one of them will cancel out. And the seconds is also on the bottom. It's also a denominator. So when you run this in your calculator, you should get 10 per molarity squared seconds. That's a very strange unit, but that's okay. That's the go-between to go from the concentrations to the rate of the reaction. So this is our rate law for this specific temperature. hope that makes sense. I want you to try it now. I've got a couple problems for you to try. And I would like you to give these a try. There's two problems here. I want you to figure out the rate law for what k equals for this one. And then this is a separate one. Notice it's a different equation. Don't let these equations toss you up. Remember, they're just different equations. These coefficients aren't really any relevance here, but what you need to know is that these are different equations. So figure out what the rate law is and what k equals for the first one, and then also what the rate law and what k is for the second one. I'd like you to give that a try, and if you want to know the answer, if you don't want to know the answer, pause it right now and give it a try. And if you're still here, that means you do want to know the answer. And here's the answers to both of them. And I would say pause it right here and see if you can solve these and get these answers. Highly recommend. Try it. See if you can get these answers. And if you don't, the rest of this video is I'm going to show you how I got these answers and kind of walk you through it. So pause it now, give it a try, and then if you don't get this, watch the rest of the video. That's my advice. But if you just like hearing my voice, then keep watching. Now, seriously, pause it and try. All right? Okay. Let's do this. So I'm going to do the first one here. The first one was 4a plus b plus 3c equals yields d. And this was our data that we got. We had 4 experiments here. And I'm going to try to figure out, to analyze A, which experiments would I use? So for A, and so I'm going to say for A, which experiments should I use? Well, I need A to change, and so I'm going to take a look here. So 3 is definitely going to be one of my experiments because 1, 2, and 4 all have the same A. So let's look at 3 and see if we can find an example where the other ones are the same. So if I look at 3, other ones are the same. So between 1 and 3, A is doubling, B is the same, C is the same. So for A, I'm going to use experiments 1 and 3. For B, what would I use? Okay, let's see. We're going to try to figure out where other ones are not changing, except for only B. So I think 2 is going to be necessary because that's a 1 here. If I use 1 and 2, A is not changing, C is not changing, only B is changing. So for B, I'm going to choose experiments 1 and 2, right? Okay. And now for the concentration of C, let's figure out which order C is. We want to find where only C is changing and the other ones are not. So I like 1 and 4. A is the same, B is the same, but C changed here, right? So using 1 and 4, A is the same, B is the same, C changed. So I'm going to say this is 1 and 4. And that's the ones I'm going to use to figure out the rate laws. So my rate law will be I'm going to use 1 and 3 for this one here. And so it's 2. It doubled. It went from here to here. This doubled. And what happened to the concentration? So my concentration doubled, but my concentration from 1 to 3, that doubled, right? 1 to 3. And the rate didn't change at all. So that stayed the same. So X must be 0. X must be 0 for that. So we're going to say our rate equals K A to the 0 power, which means we can just omit it. A is not going to be part of this. Okay, so that's A. Let's take a look at B. We said 1 and 2. So as it doubled 0.5 to 1, it looks like the rate doubled 1.1 to 1.2. So as the concentration doubled, the rate also doubled. That means X must be 1. 2 equals 2, so 2 to the first power is 2. So that would mean that B is first order. I'm going to put a little 1 there just as a reminder for us. You don't have to do that, but I'm just going to do that to kind of help us remember the orders. And then for C, we're going to do 1 and 4. So 1 and 4. As C doubled, it went from 1.1 to 4.4. So 1.1 to 4.4, the rate quadrupled. So as the concentration doubled, the rate quadrupled. So therefore X, I should probably put XYZ, but anyways, equals 2. This is a second order reactant. So that would mean that C is second order. Now when we write that, we don't need to put the 1 and we shouldn't include 0 at all. So the rate law for this is the rate equals K times the concentration of B times the concentration of C squared. So that's our rate law. Okay? The last thing we got to do is solve for K. To solve for K, we're going to substitute any one of these equations in there. So I'm going to slide this up. And let's just use 4 because it's on the screen still. You could use anything. Whatever you use is fine. You should get the same answer as what we did here. So rearrange this. I cross multiply. I'd say K equals rate over BC squared. So I'm going to say K equals rate over concentration of B times the concentration of C squared. Okay, so that's what the rate is. So let's put this in there. So the rate is 4.4, and the units is molarity per second. So 4.4 molarity per second. Okay, that's the rate. I'm putting that second on the bottom. And that's going to be multiplied by B. And so I'm going to multiply that by B. The concentration of B is 0.5. So that's 0.5 molar. And then I'm going to multiply that by C squared. So C squared, I'm just going to write this out so it's a little bit more obvious. I'm going to say it's 0.4 molarity times 0.4 molarity because it's squared. And when you square it, don't forget that that includes the units too. So it's molarity times molarity. So I've got the rate molarity per second, and then I've got B, and then I've got C twice. Okay, one molarity cancels out with one of the molarities. And now let's plug this in the calculator and see what we get. So we've got 4.4 divided by 0.5. It's easiest to do it in steps if you're not comfortable with your calculator. Just do it in steps. Say equals, and then just do it again. Divided by 0.4 divided by 0.4. So when I do this, my answer comes out to the constant equals 55, and there's no units up top, is there? It's 55 per meters, molarity squared, 2 molarities, seconds. So molarity squared seconds. So there's my answer. I got my rate law, and I've got my K for that. So that's how I worked it out. Now let's give it a try another time for the second one. Second one's a bit more challenging. So in this one, we've got A plus 3B yields 2C. And this will have our data for this one here. And the first thing I want to do again is figure out which experiments we're going to use to analyze each one. So let's take a look here. So I'm going to say for A, I'm going to use which experiments here. All right, so for A, I see a change in 3. And for A, 3 is getting bigger. I don't see it. B's the same. Check this out. Tricky, huh? So A's getting larger in this one, and if we use these ones here, only 1 and 4. Oh, never mind. There we go. Okay, 3, I would use, for A, I would use 3 and 4. Because A is getting big, as A is changing, but B is the same, and C is the same. So for A, I'm going to use 3 and 4. Now I'm going to solve right now for A. I'm just going to solve because I think I might need a little bit more room on this one, and I just want to show you something. So you're welcome to solve each one at a time. That's what I'm going to do on this one here. So if you look here, I don't know, the rate doesn't seem to have doubled. I don't know what's going on. So we can set this up mathematically. Take the larger value and divide it by the smaller. So if it doubled, let's say 1 to 2, we put 2 divided by 1 and we could see that's doubled. So let's just do this right here. So I've got the concentration of this one here. The concentration is the large one. We're going to say 3 over 4. So I'm going to say 3.125 over, that's molarity, over 1.250 molarity. That's my concentration. And when I do that, let's figure out what the concentration change was. So it's 3.125 divided by 1.20. And I see that the concentration, it didn't double, it went up by 2.5. Went up by 2.5. Okay, now let's see what that did to the rate. Okay, since I put this one on top, right, I put this one on top, then I need to put that rate on top when I'm comparing the rates. So let's put 0.5 over 0.2. So 0.5 divided by 0.2, and we get, well, hey, take a look at this, guys. Isn't that fortunate? That as the concentration went up by 2.5, the rate went up by 2.5. So I think it's safe to assume that you can understand this, that the rate law for this would be 1. The rate law for A is 1. So we can start this off. Rate equals K times the concentration of A. And that's to the first power, so I'm not going to put anything that time. All right, let's take a look, and that is for A. Let's do the same thing for B. Concentration of B. Okay, let's look at B changing around. I like 2 and 4. I see 2 and 4. I see 2 and 4, A is the same. 2 and 4, C is the same. But 2 and 4, B has changed. So let's use 2 and 4 to analyze B. Okay, I see that it tripled. So, because again, the concentration was 1.5, it tripled over 0.5, 0.5. So I'll just do it in the calculator just to kind of go through the steps. 1.5 divided by 0.5, and that's 3. So what we did here is the concentration tripled. We'll say this one's Y. Now what happened between 2 and 4 with the rate? So the rate went from 1.8 to 1.2, or 0.2, and the rate went up by 9. So 3 to what power is 9? That would mean Y equals 2. B is a second order reactant. So B is a second order reactant. Okay, next one, C. Let's take a look at C. And we've determined, we didn't determine yet. Let's do that right now. Okay, we'll do concentration of C. Do that one next. For C, let's take a look here. C. I like 1 because it's changed and these ones have not. C. 1 has larger C. Okay, 4. Okay, 4. So between 1 and 4. If we look at 1, it's it's the same concentration. If we look at 4 for A, and for B it's the same concentration, but for C the concentration changed. So let's use these ones to analyze this. So we're going to use 1 and 4, and let's just do this again. Let's take a look at the concentration between 1 and 4. So we have 2.5 over 1.25. That's the change in concentration. So 2.5 divided by 1.25. So in this situation, the concentration doubled. So the concentration doubled, and this is going to say to the z power equals, and now let's again, we're looking at 1 and 4, and it's always good to write this down, guys, so you remember which ones you're analyzing. So we're looking at 1 and 4. The difference here, take a look. Between 1 and 4, the rate didn't change, so as it doubled, the rate didn't change, therefore z equals 0. So our rate law, C is not going to be included there because Z is a zero order reactant. Very good. Now, last thing we got to do is solve for K. So K equals the rate over the concentration of A times the concentration of B squared. That's what the rate is. So let's just block this out, mixing numbers all over the place. So K, my pen's dying, guys, equals, let's just choose any reaction. Let's just, I don't know, let's use the first one. So rate would be 0.2 molarity. And here's our units. Don't forget, use the units that are here. Molarity per second divided by A, which would be 1.25 molarity, divided by B squared. So that would be 0.5 molarity and 0.5 molarity. Ran out of paper, guys, and 0.5 molarity. I ran out of paper here, kids. Okay. The molarity cancels with one of the molarities, so we have nothing on the top, and we have a second and 2 molarities on the bottom again. So let's try it out. 0.2 divided by 1.25 divided by 0.5 divided by 0.5 equals K equals 0.64. There's nothing on top, per molarity squared seconds. So here is our answers. Let's make it pretty. Pretty time, guys. There's our answers right here. Okay, we got our rate law, and we've got our K value. And that would be the answer for that question as well. So give these a try, guys. Practice them up. Make sure that you practice more than once. Don't look at the answers. Take a little break and see if you can solve it again and do it again. I mean, I do these things all the time, and you see I'm still thinking it through. When you think it through, you get the process down, you'll be able to answer these on the tests and quizzes. Okay, you gotta practice though. This is just something that's just not natural. It's not that hard with a little bit of practice. Trust me. You can do it. I'll talk to you soon. Peace.